Počnem. Okay, welcome to this mini-series of lectures on categorical logic. Let us start with the definition of a topos. A topos is going to be a universe where categorical logic is going to be interpreted and realized. So we should learn somehow what these toposes are like. So you should think the simplest topos is the category of sets and just functions between them. And this is where you normally interpret first-order logic. And here, what we want to do, we want to expand the class of kind of universes where we are able to develop logic and develop mathematics within. So in order to develop logic, you need your universe to have certain constructions, to have the ability to define certain constructions inside. So that's why we want a topos to be something fairly nice. So a category is an elementary topos if it has finite limits. This is equivalent to saying that it has pullbacks and terminal object. So pullbacks are basically just what people normally call fiber products. So something like this. And then you want to be able to complete this square by constructing some kind of fiber product, and it has to have a universal property. So for any other object U that maps like this, there should be an arrow like that. So it's also Cartesian closed. For all x and y and z, you have this kind of function space. So this bracket yz should be thought of as kind of space of functions between y and z. Now, why, you might say, in usual kind of category theory, you would consider something like Hom yz. But you see, Hom yz is just a set. And because we want to develop logic inside another universe, we need every single construction to belong to that universe. So if you're working in some arbitrary category E, you are unable to work with sets because sets are not in there. So you require this internal Hom to be inside your universe, and it has to satisfy this kind of Hom tensor duality and this is what we call internal Hom. Okay, so when you have internal Homs like this for every x, y, z, you call the category Cartesian closed. Next property is that the category E has a subobject classifier, omega. Now, in set, this is, so in the category of sets, omega is just the kind of set of truth values. You should think of maybe this as false and true. And subobject classifier is basically something that allows you to speak of characteristic functions of sub-objects. So basically, you know, this looks rather intricate. So okay, it has this subobject classifier omega, and the morphism true, which basically, you see, in set, terminal object is just a singleton, and true is the function from the singleton to omega that simply takes, okay, so maybe it is better to call them true, false and true. Okay, and then, so for every kind of subset, sub-object in the category of set is just a subset, you want to be able to construct the characteristic function of y by saying it is 1 when, or true, when x is in y, and false when x is not in y. Now this is just stated in a kind of general way in an arbitrary category. So, typical examples of topoi are Grothendieck toposes, which are categories of sheaves on a site. So I'll follow with a couple of examples, and I'll discuss sheaves in a little bit more detail just in a moment. But the important thing is that, Grothendieck topos is elementary, so therefore it is an instance of a topos. So the category of sheaves on a site is a topos. Now, examples. I already mentioned the category of sets as a typical example. Then maybe the next in complexity is pre-sheaf toposes. So what are those? If you have C, a small category, then you consider the category of pre-sheaves on C, which is simply the category of functors from C op to set. Okay? So any functor, any kind of contravariant functor from C to set is a pre-sheaf, and this is considered a category. Objects are functors, and morphisms are natural transformations between them. So these are also examples, and somehow the reason why these are examples of topoi is that this kind of functor category inherits good properties from this set. So the fact that set is a topos passes through the functor category into sets. Now, something more familiar to algebraists or just classical mathematicians. If you take a G, a group or a monoid, then you consider BG the category of all sets with action of G. Okay, that just means that you have a set together with a morphism mu from G cross X to X, satisfying the usual properties of being an action, where you write, typically in mathematics, you would write G dot X for mu Gx. Now, so what I'm doing at the moment, I'm sort of writing a monograph on example number 3, where I'm talking, in fact, about Bn, where by n I mean the monoid n plus. So these are what I call difference sets. And you can also think of them, you see, the action of n can be encoded in the action of sigma. So if x is an n action, you can sort of think of x as a difference object where sigma x is just a self-map which is the action of 1. Sigma x of an element, little x, is just 1 on x. And so this is a translation mechanism between sets with an action of monad n plus and what you might call difference sets. And this connects to difference algebra. And also dynamical systems. So a very basic example, when you think of it in a kind of topos theoretic way, can yield completely new area of mathematics. Okay, now let me maybe try to explain what these categories of sheaves are. So the simplest way of explaining sheaves is through sheaves on a topological space. So if you take a topological space X, you could also take a locale. So locale is a sort of pointless topological space. You see, topological space is a set X together with a kind of frame of open, some kind of lattice of open subsets. And a locale is simply, you kind of omit the set. You don't need the set, the underlying set. All you need to retain is the kind of structure of a frame of opens. So you could take an arbitrary frame, so that this is an algebra definition, and you just declare that locales, the category of locales is the category of frames op. And why is that? Because if you have a continuous map from x to y, that in fact gives you the kind of pullback map from omega y to omega x. So the arrows of frames go the opposite ways of arrows of underlying sets. So, okay, it doesn't matter. This is somehow useful when you are working in an arbitrary topos, because in an arbitrary topos you cannot have the underlying set, because we don't have access to sets. We're working in a kind of abstract category E. So, all right. So, but you can just think of a topological space X. Now, what are sheaves? Well, what I wrote here is that a sheaf is, first of all, a pre-sheaf. So a sheaf is just a kind of pre-sheaf on the frame of opens. And, so this is kind of in the way, isn't it? Can we minimize the, so basically for, it's a pre-sheaf, which means that for every U open, you have the set f of U, and elements of f of U are called sections. of the pre-sheaf. And a sheaf is a kind of nice pre-sheaf which admits unique gluing in the following sense. So whenever you have an open covering of an open set, then every compatible system of local sections, so you see these sections Si are on these smaller subsets. So you have your big set U, which is covered by these Ui, Uj, and on each of these smaller subsets, you take a section. Now, these have to be compatible because you want to glue them, right? And unless they agree on intersections, so if you have a section Si on Ui and Sj on Uj, in order to be able to glue them, they must at least agree on the intersection. So whenever you have a collection like that, this is what it means to be compatible, then they glue uniquely to a global sections. So you can glue local data into a global datum. Topologists invented this because they work with kind of manifolds, such as a sphere, and you often want to kind of cover a sphere with, or a manifold with charts, and often the question is like, can you glue local data, which is given on these charts, into a global datum, which is given everywhere on the manifold? So this is why sheaves were kind of invented by topologists. But it turns out that you can make sense of this in a much more general situation. And Grothendieck realized that you can generalize the situation not just from topological spaces to locales, but even further to sites. So what is a site? A site is a pair consisting of a small category C and a coverage on C. So how to think of coverages? Well, a coverage prescribes for each object of C which of the families of morphisms with target U are coverings. You see, in a topological space, that would obviously be when the union, so in a topological space, all these morphisms would be just inclusions of open subsets, and the condition for this being a cover would be to say that the union of all the Ui equals U. Okay? But you can, generalize this and think of it very abstractly. You just need to prescribe in a certain consistent way which families you consider covering families. They have to satisfy somehow very general analogues of being a topology. But this can be done, and definition of sheaves still makes sense. So I gave you sort of a definition of sheaves on topological spaces, but a very similar definition will work on an arbitrary site. And this way you get a category of sheaves. Morphisms between them are natural transformations, just as pre-sheaves. Okay. And of course, sheaves on some site C are, in particular, pre-sheaves on C. Okay. Now, this is the kind of universes that we want to be talking about. What are suitable morphisms between them? These are called geometric morphisms. So, a geometric morphism, f between two toposes, f and e, is, well, it's not really something. It's actually a pair of functors, f upper star and f lower star, which are adjoint. So this means that f upper star is left adjoint to f lower star. And I'll explain in a minute what's the kind of intuition behind this. Further, a geometric morphism is called essential if we have another functor, f shriek, which is a further left adjoint of f upper star. So then you have a triple of adjoint functors. And if f and g are geometric morphisms, a natural transformation between f and g is in fact defined to be the natural transformation between the pullback parts. This gives you like a two-category of toposes. Example, so why is this definition meaningful, and where does it come from? What's the intuition behind it? Let's go back to the example of topological spaces. So if you have a continuous map of topological spaces or locales, then you have a direct image functor on sheaves, which is simple, very simple to describe. If you take a sheaf on X, you can produce a sheaf on Y by just precomposing with a kind of pre-image by F. So that just means that so F lower star of F of V, where V is a subset of Y, open subset of Y, is going to be F of F inverse of V. So because F is continuous map, this is an open in, maybe I should, it's maybe better to write, it's kind of more general to write V in kind of family of opens. And because F is continuous, this is in opens of X. And this makes sense. Now the other, so it's a general fact that this admits an exact, a left exact, oops, where is my pencil? Ah, yes, okay. Left exact, left adjoint, F upper star. But it's a little bit tricky to define, so I'm not going to define it. But it's a pullback of sheaves, and this is your intuition. So somehow you make this sort of situation into a general definition and consider these geometric maps. Okay. Now, it's often very important in topos theory to be able to localize or work over a fixed object. So we say that we work in the slice category. So if you take X, a fixed object of E, then the slice category, written like this, E over X, has objects which are basically morphisms of E with fixed target X, and morphisms between two such arrows are just commutative diagrams like that. So this is an object, this is another object, and the morphism between them is simply a commutative arrow like that. Now, a morphism, f from x to y, induces a base change functor from the slice category over y to the slice category over x. And the way you do this is you take an object over y, and then you add this f, which is given, and calculate the pullback, and you output this arrow here. Okay? This is an object over x, so it really lands in this category where it's supposed to. So this is a very well-known base change functor. And we have a theorem saying that for each x in a topos E, the slice category over x is again a topos, and an arbitrary morphism, f, from x to y induces an essential geometric morphism, f, from the slice categories E over x to E over y. In other words, we have the following situation. So for an essential morphism, you need a triple of adjoint functors like this. And this is what it looks like as a diagram. The leftmost adjoint is sometimes called sigma f, or sometimes f lower shriek. And then you have this pullback or base change, and then the rightmost functor is sometimes denoted with pi f, and sometimes as f lower star. So this, you might think, why we're considering this, is this too kind of set category theoretic and boring? But these guys are actually going to give us ability to interpret quantifiers, right? So, I mean, these names with sigma f and pi f should somehow remind you of something with happening with quantifiers. So, our next topic is subobjects, and basically what do the families of subobjects for a fixed object look like? So it's a fact that an elementary topos E is a heightened category, and I'll try to explain a little bit what this means. So for any morphism f from x to y in E, the top here is the diagram I just had, okay? With these, the top is this essential geometric morphisms between the slice categories induced by f. On the other hand, on the bottom, I put subobjects of x, the category of subobjects of x, and the category of subobjects of y. And you see, a subobject of x is just a monomorphism into x, but in particular, this is an object of the slice category, right? Because a monomorphism into x is an object of the slice category. So you have this kind of natural embedding there. But you also have sort of image factorizations in toposes, which I haven't mentioned so far, but basically if you have an arbitrary morphism u from A to B, you can sort of factorize it through the image of u, where this bit becomes a subobject. And this, this functor here, this sigma, is basically this comes from this image factorization. And sort of these functors on the slice categories induce the relevant functors on sub-objects. And now you can start really seeing some kind of logic appear, because the functor induced by sigma f on sub-objects is what we call exist f. Well, this one is still called f inverse. And here you have for all f. Okay, let me show you in the simplest example of the category of sets what these functors are. So you take, say, a morphism f from x to y, and then you take a sub-object a of x and b of y. The functor exist f on a is simply the what we normally call the image of a, returns the subset of b given by the set of those y such that there exist x in a, f of x equals y. And because you have this existential quantifier here, it's kind of meaningful to call this functor exist f. The preimage is just the preimage. And for all f of a, this is the set of those y in y where the fiber over y is full. So you see, you have somehow, think of this kind of, so this is your x projecting onto this y, and you have your a somewhere like that, okay? This is for this y here, so y naught. This is your a y naught, and this is the whole x y naught, right? So here, a y naught is not the whole x y naught. So this will not be in for all. So the only guy here where it's going to happen is basically here, where so maybe here have y1, and here the fiber is the whole thing, and then this will be in for all fa. Okay. So lots of this kind of logic that happens in topoi comes from the fact that the sub-object classifier is an internal Heyting algebra, which means that it has the following operations. So omega has, we already know it has the true map from before. It also has the false map. It has meets, joins, and implication. So the first collection defines a distributive lattice, and the kind of pre-order is obtained as the equalizer of meet and the projection map. You know, you basically you need to define the set of pairs where x is less than or equal to y, and this equalizer tells you that this is the set of those x and y such that x and y equals x. So it turns out that this a partially ordered set is actually Cartesian closed. You have an operation of implication whereby x and y is less than or equal to z if and only if x is less than or equal to y implies z. So y implies z is another kind of element of omega. You can define negation as x implies false. However, you don't always get a Boolean situation. So this subobject classifier is not always Boolean. I can give you maybe some example. So, you know, in the case of BG, where I spoke about the classifying topos of a group or a monoid. So BG is Boolean if and only if G is a group. So as long as it's a monoid which is not a group, it's not Boolean. And my case of different sets is definitely not Boolean, and a lot of difficulty in that area arises from this fact. So, okay, now the structure of toposes that I defined so far is basically enough to interpret a great deal of logic. I've just kind of constructed these functors which will allow us to talk about quantifiers and so on. And however, you can select bits of these operations. So instead of working with, you can be working with kind of smaller fragments of logic, and then smaller fragments of logic which are not allowed all the connectives can be interpreted in corresponding type of category. Okay, so more generally, in so-called regular categories, you have finite limits, which means that you can talk about equalities and relations, because to talk about equalities, you need to be talking about equalizers, which are finite limits. And the lattices of sub-objects have intersection. Exist F functor also makes sense and satisfies Frobenius reciprocity. So this kind of Frobenius reciprocity appears all over mathematics, and it's quite often quite useful. Now, so regular sort of corresponds to a fragment of logic where you can use relations, equality, joins, and existential quantification. Now, in coherent categories, so these are regular plus subobject lattice also has finite unions, and finite unions are stable under pullback. In geometric categories, so these are coherent plus you have arbitrary unions, arbitrary small unions over kind of sets of indices, which are also stable under pullbacks. And example, Grothendieck topos is a geometric category. So Grothendieck topos has all these constructions. Whereas, okay, elementary topoi don't necessarily have arbitrary unions. Right. Okay. So let me speak now about the syntax of first-order categorical logic. So it's very similar to what you know about first-order logic from before. You have first-order signature, sigma, that consists of sorts. I usually call them kind of A, B, and so on, AI, BI. You have function symbols, and you see function symbols can act on a combination of sorts and land in a sort. So for the moment, this is just a list of sorts, which tells you somehow kind of arity of the function. And you have relation symbols, again, R, which is, it's indicated that it's a relation on this sort of list of sorts. What do terms look like? Now, for each variable, you indicate the belonging to a sort by saying x colon A. So that just means that x is a variable of sort A. And when you have a function symbol, f from A1, AN to B, and you have terms, a term 1 of sort A1, term n of sort AN, then you are able to apply f to these terms, and what you get is a term of sort B, okay, because f maps from this list into B. So this is all familiar if you've seen an inductive definition of first order formulae. All right, so what do formulae look like? Relations, if you have a relation which acts on the sorts A1, AN, and you have terms T1, A1, Tn of sort AN, then R of T1, Tn is a formula. If you have S and T terms of the same sort, then you can have equality, S equals A. But this of course is equality in the sort A. That's why I wrote kind of S equals subscript A. True symbol is a formula, and if phi and psi are formulae, you can have binary conjunction, falsity, binary disjunction, implication, negation, existential quantification, where you need to indicate over which sort the existential quantifier goes, and then universal quantification. And now beyond first order, you can also allow infinite disjunctions of a particular type. So the index set has to be set, and somehow you can't have an increasing number of free variables. So the number of free variables must be finite in total, but you can have an infinite disjunction of formulae, and sometimes even infinite conjunction. Okay, so now we have all these possibilities, but we're going to focus on certain fragments of logic which can be obtained by only applying some of these inductively. So atomic formulae are closed only under 1 and 2. So let's see, 1 and 2, relations and equality. Horn formulae 1 to 4, I'm not interested in those for the moment, so I'll leave them. Regular 1 to 4 and 9. So basically these are relations, equality, truth, binary conjunction, but no disjunctions, and existential quantification. And coherent, or sometimes called positive logic, allows 1 to 6 and 9. So you also allow conjunction, falsity, and disjunction, and existential quantification. But you haven't got implication, and you haven't got negations. First order allows everything, 1 to 10, but not the infinitary disjunctions and conjunctions. Geometric logic is particularly interesting for us, and it's basically the same as coherent, so positive logic, plus infinite disjunctions. And infinitary first order would be to allow all these. Okay, now we need to be speaking about a formula in context. So usually in first order logic, you explain what free variables are of a formula, but somehow here we sort of want to list a certain number of free variables and their sorts, and then this symbol will indicate that free variables of phi are among the given ones. The reason we do this is because if you say have I don't know, phi of x in A, and you want to kind of construct a realization, you don't know whether the realization should be somehow one-dimensional object, or you could, or maybe you can also think of this as a formula in two variables where the second variable doesn't appear. And then the realization of that one would be kind of two-dimensional, right? So this is why we kind of fix the possible list of variables, and then we kind of indicate that by this symbol that free variables of phi are among the given list. A sequent is just a symbol like this, where you indicate that the context where phi and psi live, and the intuition behind this is that secretly you want to be talking about implications, even in geometric logic, but you are not allowing nested implications. You want to allow only one kind of level, outside level of implication. And so we introduce this symbol for sequence. But secretly, we are thinking of implication phi implies psi. And now a theory over the signature sigma is a set which we usually denote T, boldface T, of sequence. And you can be speaking about a regular theory, coherent theory, geometric theory, first order theory, depending on where the sequence come from. So, a sequent is regular if phi and psi are regular. A sequent is geometric if phi and psi are geometric. Okay. Examples. Algebraic theories are usually single sorted. They have no relations, and they are atomic. So some kind of algebraic structure like monoids, groups, rings, abelian groups, are modules for a given ring object R, Heyting algebras, etc., etc. Many sorted algebraic theories include modules where you can now vary the ring and the module, right? So here I fix the ring. Here you allow kind of pairs Rm, where M is an R module, directed graphs, etc., etc. Horn theories include posets, ordered groups, ordered rings, torsion-free abelian groups. You see, you can say torsion-free abelian groups because you have... no, okay, no, sorry. For torsion abelian groups, you need infinite disjunction. Torsion-free, you can say, even for Horn theories. Okay, coherent, which will turn out to be very interesting for us in the next lecture. Local rings and fields. Geometric theories, you can talk about torsion abelian groups, and here you really need infinite disjunctions. You need to say somehow that for every element either is of order 2, or is of order 3, or is of order 4, and so on. So you need to say, you need to have a infinite disjunction, which first order logic cannot axiomatize. Fields of finite characteristic, a similar thing, you would have an infinite disjunction. Strict local rings, which were explained by Gavin Wraith, which will give us, again, some important algebraic geometric applications in the next lecture. Okay, so now that we have syntax, let me explain how we interpret all these elements, so all these formulas. A sigma structure M in a category C with finite products. So you need at least finite products to interpret a sigma structure. And the reason is that, okay, for each sort A, you need to give an object MA. So far, so good. For a list A1AN of sorts, the interpretation of that is just the product of MA1 cross 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 MAN. And this is where you need products. Okay? This is where, yeah. And for a function symbol from the list of sorts A1, AN to B, the interpretation is C morphism, so a morphism in the category C called MF, which goes from MA1AN to MB, where of course we know from before that this is just the product here. And similarly, if you have a relation symbol, this is in fact interpreted as a subobject in the category of C of MA1AN. Okay, then I think we're kind of slowly running out of time, so I'll kind of maybe start skipping things. A sigma structure homomorphism between two structures, M and N, is given by actual morphisms in C between MA and NA for all sorts, and such that for every function symbol you have the following commutative diagram, which is the most natural thing. So this is given to you by the interpretation of F in M, and this is given to you from the interpretation of F in N. I forgot to write here that this is NF. And here you just have a product of these morphisms, and this is HB, and this is supposed to commute. and similarly for relations. This gives you so the kind of collection of sigma structures and sigma structure homomorphisms gives you a category of sigma structures inside the category of C. And now you're able to start interpreting terms and formulae as well, but for each of the connectives, for each of the new connectives, you're going to need higher and higher kind of properties of the category. Okay, you can no longer get away with just category with products. So, interpreting terms, given a term T in free variable X and sigma structure, the interpretation of that is a C morphism denoted like this. So this is what we denote interpretation in M, and obviously it should go from M A1 A n, where these variables live, and it lands in MB, and it's defined inductively following the syntactic definition of terms. So if you have a particular variable inside a list of variables, then you have a situation. So these variables kind of correspond to this product, and this variable corresponds to one of the factors, and the interpretation of this term is simply a projection to the ith factor. And if you have a term obtained by applying the function symbol, then you can you can interpret it as this composite. So obviously all the free variables are kind of contained on this product of these sorts, and then applying terms gives you maps into from MA1 to MC1 and MAN to and so on, and then you can combine them and get a map here, and now you have the interpretation of F, and you land in MB, and this is this now gives you the interpretation of F. Okay, so for interpreting formulae, so is it okay to go for another like 5 minutes? All right, so to interpret formulae, intuition is, as I already said, a regular or coherent or first order or geometric formula phi can be interpreted in a corresponding type of category because you have available constructions to interpret the relevant connectives. So, okay, now if you have a formula in context X, and these variables xi are of sorts ai, and then you have an M structure, the interpretation of this formula is going to be a sub-object of the relevant interpretation, the product of these objects here. And it's defined inductively. So, in any case, the important thing to remember is that the interpretation is going to be a sub-object of some product of sorts. Now, if you simply have a relation applied to a bunch of terms, then, okay, let's see what's actually given. So terms give you the bottom arrow, relation gives you this arrow here. This is the interpretation of the relation. And then you can take the pullback and you get this interpretation here, and it is what it is a subobject of MA1AN as it's supposed to be. Okay, so this is given from the interpretation of terms. This is given from the interpretation of the relation, and you construct the pullback. When you have equality of terms as a formula, then the interpretation of that is going to be the equalizer of the corresponding morphisms in C. And 3 to 8 are basically these logical connectives, and or implies and not, and these use the Heiting algebra structure of subobjects, in the sense that the interpretation of phi and psi is the kind of intersection in subobjects, and or goes to union, and this goes to kind of Heiting implication, and so on. And what's most interesting is the quantifiers. So if phi is obtained from psi using an existential quantifier, then the interpretation is obtained by the application of this exists pi functor, where pi is the appropriate projection morphism. And similarly, if you have a formula with a universal quantifier, then the interpretation is going to be obtained by applying the functor for all pi, etc., etc. So if you have a geometric category, that means you have infinite unions of subobjects, so you can do this. And for a sequent, phi implies psi, we say that the structure M models the sequent, provided the realization of phi in M is less than or equal to the realization of psi in M, where this is the kind of posset structure of the lattice of subobjects. And you say that M models the theory T, provided M models all sequence of the theory. This gives rise to the category T mod in C, and this is the full subcategory of sigma structures in C whose objects are models of T. Okay, so I think this is okay. The example is complicated, so I'll leave it for next time. All right, so this is maybe a good point to stop. You now know how to construct a category of models of a geometric theory, or even first order theory, inside a topos. Okay, thanks for listening, and we'll continue tomorrow with classifying toposes, etc.